Wi-Fi here. All right, line diagram of this. So decane, just as a reminder, you put your pen on the paper. That's carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons represented right there. So, although when you're given a molecule, you have to figure out where is carbon number 1. You have to look at it to see that. When you're drawing a molecule, you can, you can decide to start over here. This could be carbon number 2 if you want it to be. But we read right to left, or left to right. So I usually call that carbon number 1. So there's a methyl group on number 2, 3, 4, 5. So there's 2, 4, 5 trimethyl decane. All right, there aren't any other substituents on there. That's it. Oh, I could have also done attendance during that time. Natasha.
Here.
Well, let's see here. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. You're all here. It's the way to do it, folks. We can learn more chemistry that way. All right? So everybody's here. Okay, what we need to add to what we've learned already is isomers. We need to understand what we mean when we talk about isomers. We need to talk about cycloalkanes. What's the difference between a aliphatic or chain alkane and a cycloalkane? And then we need to cover reactions. All right, just to point these out, here's so what do we have here? Okay, here's a methyl, just one on the second carbon here. Here's an ethyl on the 1, 2, 3, the third carbon there. So this is going to be carbon number 1, 2, 3, 4, 5, 6. Is that right? Now wait a minute. 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6. Okay? Always check yourself. Here I am. I'm just kind of thinking that's the longest chain, but we got to make sure it is. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It wouldn't matter. It really wouldn't matter. This could be 1, 2, 3, 4, 5, 6. And what would I have? I would have an ethyl on carbon number 4. And if I do 1, 2, 3, 4, 5, 6, what do I have? I've got an ethyl on carbon number 4. Okay? So it doesn't matter. We can make that carbon number 4, and that's carbon or number 5. And that's 6. And so what I've got here is an ethyl on 4 and a methyl on 2. And we're doing it alphabetically according to the name of the substituent. So 4-ethyl, 2-methyl hexane. And we are putting dashes. So I want to see dashes between your numbers. You see we got an L right there. Looks, an L and a 1 look the same. So we don't need a dash here. That's an L. And I don't care whether you put a space here or not. It doesn't matter whether you put a space there or not. But there's the name. Now let's see what we've got here. 1, 2, 3, 4, 5, 6. And there's carbon number 2. So now this is oriented the opposite of over here. And here I've got 1, 2, I'm going from right to left, but here's 1, 2, I'm going from left to right. But this is the line diagram of that molecule. It could have been 1, 2, 3, 4, 5, 6. I mean, it could have been that. It's 2, 3, and it could have been that. That'd be fine too. 1, 2, on number 2 I got a methyl. 3, 4, on number 4 I have an ethyl. Notice that an ethyl has a kink in it. It's got a bend to distinguish it from a methyl group. The ethyl has a bend in it. And this little symbol here means we are recording. And see, every so often I hit that, and okay, everybody, smile. You smiling? and so every so often you'll see my shoes, because I'm going to have to keep my shoes polished, because I have inadvertently hit that. Okay, I put it into the camera mode. All right? So that was fun. Okay, just a couple real quick examples, and we'll go on because we need to cover isomers and other things. But 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Here's another case where it doesn't matter whether I go up there or whether I go down here. I'm still, whatever I do, now remember, when you find your longest chain, then the next, that gives you your parent name. 1, 2, 3, 4, 5, 6, 7. That gives you this name, heptane. Okay, heptane has 7 carbons in it. This molecule has 7, 8, 9, 10, 11 carbons in it, right? So heptane has left out, the name heptane has left out 4 carbons. What are they? Those are substituents. All right, so we got to pick up those other, you now have to include in the name everything that was left out of the parent name. I mean, heptane is just 7 carbons long with 16 hydrogens on it. So what did we leave out? We left out 2 methyl groups and an ethyl group, and this is on carbon number 2. This is on carbon number 3. This is on carbon number 5. So I got 5-ethyl dash 2, 3, 2, 3 dash dimethyl heptane. All right. You can see that D comes before E, but we're not alphabetizing off of that. We're not alphabetizing off of this prefix. We're alphabetizing off of the name of the substituent. So di, tri, tetra, you don't use that to alphabetize. You use the ethyl, the methyl, the isopropyl, the propyl, the butyl. So a butyl will come before an ethyl. All right? I'm just trying to make a few points here so when you hit some of these different things, let me just, let's just say for a second, okay, so that's the name of that one, all right? That's the name of that one. So now let's do something here. Let's pretend that's just a hydrogen there, and let's move that one over to there. I just want to show you something here. Okay, now what we have, we still have 2 methyl groups, but they're both on the same carbon. Well, we would have to get rid of that hydrogen right there. Oh, I know what we do there. We come up here and we look at our colors. We get rid of that hydrogen. Okay? So now we got 2 methyls on what? The second carbon. So this is going to be 5-ethyl dash Now I'm going to put 2, 2 dash dimethyl. Don't just put 2 dimethyl. If you have a di here, you should have 2 numbers here, even if they're the same number. All right? If I see a prefix di, then you need to tell me where both of them are. Why would you just not leave 1, 2? If you left 1, 2, I would be scratching my head saying, is the second methyl on carbon number 2, is that what they meant? Or is it somewhere else on the molecule? In other words, when you use this, you need to specify where both of the methyls are. If you use tri or tetra. So tetra should have 4 numbers. If it's a tetramethyl something, it should be 2-3-4-5 tetramethyldecaine. Okay? There's a number for every substituent. Okay. All right, I'm not going to, this one actually has a substituent on there that I didn't require you, the isobutyl substituent. Butyl has 4 possible substituents, and I've had you learn N-butyl and tertiary butyl. Those are the 2 butyl substituents that I'm requiring you to be familiar with. Here's a third one. There's isobutyl, and there's also secondary butyl, but we won't get all hung up in all the butyls. All right, we're just this is kind of review, but applying what you now know to some more complicated molecules. Look at that complicated thing. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, wait a minute. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So that isn't the longest chain. That isn't the longest chain. Let's try this. 1, 2, 3, 4, 5, 6, 7, 8. So even that is not the longest chain. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. And we can see over here, 1, 2, 3, 4. By the 4th carbon, we have this. What is that? What is that? No. What is that? That's a substituent. This is their secondary butyl substituent over here. That is an isopropyl group. That's what an isopropyl group looks like. It's not a propyl. A propyl is 3 carbons in a row, and it would be attached here. This is an isopropyl. And it's attached right here. But don't forget there's a hydrogen on that carbon. You see there's a hydrogen on that carbon right there. So that's an isopropyl group. There's your secondary butyl group. That's the other butyl. I'm not going to get bogged down in the whole name of that thing. You can see we found that it was 9 carbons long, so it's nonane. All right, there is this slide. You might want to print that one off. I don't know, but have that one handy. Those are the 6 rules all in one slide. We went down through those rules individually as we learned how to apply them, but here they are all together. Okay, any questions? Yes?
When we count can you go back to slide real quick?
Right here?
Yeah, I thought you said when we count we start from the right.
No, I said, what did I say?
Longest chain.
Well, we find the longest chain, but then where do we start counting?
From the one closest.
The end that will get us to the first substituent. The end closest to the first substituent. So let's see if this one is 1. 1, 2, 3, 4, 5. That would make this carbon number 5. 1, 2, 3, 4. You see, I'm getting to this substituent by the 4th carbon. So this is carbon number 1. All right, there is a particular end to start with, and it's the end closest to the first substituent. Good question. I've hit you with a lot of different parameters here, so now you need to piece them all together, right? And not get them tangled up in one another. So that was a good question. All right, we start from, you don't always start from the right or always start from the left. You start from whichever end is closest to the first substituent. Okay, let's draw, well, you did this on your homework, didn't you? And we just did that here. So a lot of what we did last Monday or last Wednesday and just now is go from a molecule, a structure, and find a name. On your homework, I gave you the name of some compounds, and I said draw the structure. And the way to work at that is to start with the parent name. We did something like that right there. There's the 2,4,5-trimethyldecane. So we started with decane. We put the decane out there. So pentane 1, 2, 3, 4, 5. And we got a 2, 2, 4 trimethylpentane. There's the line diagram. Oh, well, let's do this 3-isopropyl hexane. Wish I could get myself more space right here. 3-isopropyl hexane right here. So, and let's do the structure. Go ahead and draw the structural formula. We won't do all 3 of these, but do the 3-isopropyl hexane. Draw the structural formula of hexane. The last thing you want to put on your structure are hydrogens. Don't put your hydrogens on until you have the structure, the substituents, and then fill in the gaps, anything that needs to have a hydrogen after that. Okay, so there's hexane, and 6 carbons long. So on the 3rd carbon, you're going to put an isopropyl group. And this is why in chapter 10, I do want you to put all the hydrogens. So this is going to have 3 hydrogens on it. This is going to have 3 hydrogens on it. And this carbon here, you see, if you just left that there, there's only 1, 2, 3 bonds right there. So you need another hydrogen right here. And then you would just finish this off. Well, let's do all three of these. Was this one of your homework problems? No? Okay. Well, so hexane, let's do the line diagram down here. 1, 2, 3, 4, 5, 6. So on number 3, well, okay, there's 1, 2, 3, 4, 5, 6. There's hexane. So what would an isopropyl group look like? Well, it's going to look like that. That's what an isopropyl group would look like. It doesn't matter whether it's on the top or the bottom. Yes?
How do you know, like, why did you put it right there? Like, how do you know?
Because that's the third carbon. I put it on the third carbon. It's 3 isopropyl.
And
So
it doesn't matter if it goes on the top or bottom, so you can put that, where you put that 3, you can put the line up and.
yep. Could go like that.
Yeah.
I just thought it looked prettier going underneath.
Yeah, it totally does.
Yeah.
So, like, does it ever matter, like, if you put, like, a methyl, like, up or down? Like,
No, because, let's say there were 2 methyls right here. Let's say there were 2 methyls on that carbon. One would have to go up.
I have another question.
Yeah.
What about when you're doing the structural formula? Like if the isopropyl, instead of putting it at the top, what happens if you put it at the bottom? Does
That-
that change it? Or just-
No, that doesn't change it.
Oh, okay.
Because here's what to keep in mind. What we're trying to keep in mind here, it is structure. So there's 5 carbons. There's 5. See if I can get a 6th one on here. There's 6. There's 6, and here's a methyl, right? So I don't have that molecule necessarily, but this should suffice. There's hexane, and so there's the methyl group on the top. But I told you that these bonds can rotate. Okay, there's the methyl group on the bottom. We haven't changed the structure by drawing it on the top or the bottom. Just make sure it's on the right carbon. If this is 2-methylhexane, this is 2-methylhexane. 2-methylhexane gets into all those configurations. All right? Now we're not going to just draw, if you wanted to try to confuse your audience, you could go, here's the carbon, there's a carbon, there's a carbon there, and there's a carbon there. 1, 2, 3, 4, 5, and there's another carbon there. That's hexane. Okay? It's kind of confusing. Uses a lot of paper. And I could twist this molecule into that shape. I could actually twist this molecule into that shape. It's still hexane. It's still hexane. But when we do draw it, and we're trying to communicate to someone what molecule we're talking about, we're not going to try to tie it in a knot. So they have to kind of stand on their head to figure out what you're trying to talk to them about, okay? But it doesn't matter whether it's on the top or whether it's on the bottom. It can easily get into both of those configurations. Just make sure it's on the right carbon and make sure it looks like what it's supposed to look like. These are methyl groups, but this is an isopropyl group. That's an isopropyl group. Okay, so, all right, let's just do the condensed formula real quickly. So we've got a CH3 here. We've got a CH2. We've got a CH. And so isopropyl, we could just say this is a C3H367. This isn't good, because that could be a propyl group. That's a propyl or an isopropyl. So how do we distinguish an isopropyl from a propyl in a condensed formula? All right, let's not worry about it, since it's got me stumped. I guess what we would do is something like this. Yeah, we'd have to do something like that. CH2, CH2, CH3. Because the propyl and the isopropyl are going to be 3 carbons and 7 hydrogens. So something like that. I wouldn't worry too much about it. I don't know that I ever asked that. Isopropyl. These are the two that I have given you. Isopropyl and tertiary butyl. All right, constitutional isomers. Now, I don't know if I have enough carbons to get by here today. Maybe. Okay, here's butane. Guess I'm getting pentane here. Here is butane. This will introduce the concept of isomers. Butane. Now, what you already know about butane. Here, look, butane is N is 4. 2N plus 2 is 10. 2, 4, 6, 8, 9, 10 hydrogens. That's the molecular formula of butane. Now look over here. We have 4 carbons, but let's count the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. C4H10. Those two molecules have exactly the same molecular formula, but different structures. That's what isomers are. This is butane. This is isobutane. This molecule is not superimposable on this molecule. I just got done telling you, you can twist this molecule all around. You can rotate around single bonds. You could get it into that shape. But what we can't do is get butane into this shape. All right? Can't do it. I can superimpose 3 of these carbons on top of one another, and I mean, you can see that this 4th carbon is going to sit on top of this hydrogen. They are structurally different molecules. They have different structures. But they have the same molecular formula. That's what has to be the case. Same exact molecular formula, but different structures. That's isomers. Those are isomers. And you can see they got the same molecular formula, but they have different properties. This thing boils at around 0 degrees centigrade, 0.4, negative 0.4. So it's right about 0. This boils 12 degrees lower, negative 12 degrees centigrade. A distinctly different boiling point. It's distinctly different melting point. All right. This molecule is, this is not its IUPAC name. That's not the IUPAC name of that molecule. Pretend you've not seen that name, and I said name that compound. What would you name it? What's the name of it? It's not butane, that's butane. Propane, the longest chain, 1, 2, 3. 2-methyl propane, right? You apply the IUPAC rules, find the longest chains, 3 carbons long. Parent name is going to be propane. It has one substituent on it, on the second carbon.
Oh.
It's 2-methylpropane. All right, so that proves another point. Here's the IUPAC name of it, 2-methylpropane. Isomers don't have to have the same name. This is butane. You say that's propane. How could that be an isomer? It is. 2-methylpropane is an isomer of butane. All right, you with that? What is today? The 6th. Okay. All right. This is its common name. Common. And for that reason, you need to have a 3x5 card of this molecule with that structure. And then on the front side of it, where you have its names, put both names. It's 2-methylpropane. It's also called isobutane. I think this is the only molecule like this in chapter 10 where there is a common name for a compound that actually kind of is used more often than its IUPAC name. This is its IUPAC name. So add that. All right, let's go on from there and let's look at cycloalkanes. All right, here is hexane. 1, 2, 3, 4, 5, 6 carbons long. Hexane. Just standard old hexane that you've been learning about so far. Cycloalkanes. Cycloalkanes are alkanes where, if you see this is 6 carbons long, and I told you it can get all twisted around. It can get twisted around to where the two end carbons are real close to each other, and they can cyclize. So how would they cyclize? Well, you take a hydrogen off of that one, and you take a hydrogen off of that one, and connect the first carbon to the 6th carbon, and you still have 6 carbons, but now it's in a cycle. It's in a cycle, in a ring. This is cyclohexane. Cyclohexane. Now notice that when we did link those 2 end carbons together, we had to take off 2 hydrogens. So the formula for this changes a little bit. We go to, it becomes CnH2n. They have 2 less hydrogens. So we're going to have something like this. For a cycloalkane, you can't just say it's CnH2n plus 2. It's actually CnH2n, period. So cyclohexane has, you can see it has 6 carbons, and each one of those carbons has 2 hydrogens on it. The structural formula of that, if I drew the structural formula, I do that, and you can see each carbon has 2 bonds to it right now. And to finish it off, put the hydrogens outside the ring. Notice where they are here. They're outside the ring. There's nothing inside the ring. These models are mimicking what the molecule actually does. We've got these tetrahedral angles, and because the carbons are kind of directed towards one another, the hydrogens are left out here outside the ring. So there's 2 hydrogens on each carbon. All right. I wouldn't even worry about a condensed formula, but you're going to love the line formula. There it is right there. There's the line formula for cyclohexane. It's not a stop sign. I think a stop sign is an octagon. This is a hexagon. All right, here's a few examples. Now, you notice I started with 6 carbons, and you could get them around to each other real nicely. If I took 3 of these carbons off of here, and there's cyclopropane, you can see cyclopropane, I can't get this carbon over to there without really constraining these bond angles. All right, so cyclopropane is not a very common cycloalkane. I could get that there, but now I've gone from 109 degree angles to 60 degree angles. Isn't that the angle of an isosceles triangle or an equilateral triangle? 60, 60, 60 is 180. The internal angles of a triangle are 180 degrees. So now I got 60 degree bond angles. That's constrained. That's like you trying to get your foot into a size 3 shoe. Okay? Constrained. You can't wait to get out of those pair of shoes. You probably can't get your foot in a size 3 shoe. All right? But that's kind of what it is like. And the same way with this molecule. This molecule can't wait for those bonds to break. And that makes this a very unstable molecule. You might be able, with 4 of them, you get to 90 degree angles. 4 of them, you get to 90 degree angles. 5 of them, you can actually get back to the tetrahedral angle. 6 of them is very comfortable. So cyclohexane is a very common solvent in the organic laboratory. Just as common, maybe even more common than hexane itself is cyclohexane. This is a very, and this can get into different conformations. We'll talk about that in a second. This can wiggle around a little bit without breaking bonds. It has some wiggle room, but not as much flexibility as the hexane itself. All right, now here's cyclohexane. 1, 2, 3, 4, 5, 6 carbons, and in this case they're putting the preference on the chloro, so they're starting. That's carbon number 1, but they're going to count. We're going to count over to the next substituent on the shortest path. In other words, you don't go clockwise or counterclockwise. You go the shortest path to the other substituents. So this is carbon 1, 2, 3. 1 chloro, 3 methyl cyclohexane. All right, it wouldn't be 1, 2, 3, 4, 5. It wouldn't be right to call this 1, 5. 1 chloro, 5 methyl. You're really trying to get your numbers down to the smallest numbers. And how do you do that? You get there, you take the smallest path over to the next substituent. Okay, conformations. This is applying it to butane itself, just aliphatic or chain linear butane. It can wiggle around into different conformations. All these molecules can wiggle a little bit. They can spin around to single bonds, but on cyclohexane, be aware of these 2 specific conformations that we talk about. The chair and boat. Okay, what do we mean? Well, let's look at 4 of these carbons. Let's look at 4 of these carbons and put them in a plane. So you can see I've got a plane going through these 4 carbons. And if I bend this one down, bend the other one up, I've got a chair. Like a lounge chair sitting around the pool. There's the chair, there's the back of the chair, there's the legs. That's the chair formation or conformation. The chair conformation of cyclohexane. Now, if you bop this one up, it becomes like a little life raft. Okay? You see? It's like a little life raft. Boat. There's the boat conformation. So just kind of be aware of that. We're not breaking any bonds. We're just wiggling it into different conformations. It's probably a little more comfortable, a little lower energy for it to be in the chair because things kind of want space around them. These hydrogens are getting close to each other in the boat. And it could end up being forced into that for some reason, but it might be a little more comfortable like that. Okay. Just quickly, properties of it. Let me see. How many more slides do I have?
4 more.
1 more?
Like 4.
4 more?
Yeah.
Okay. The last couple we got to talk about reactions. Okay. Properties. All right, we're going to be using these words, polar and nonpolar, a lot in this course. So kind of get familiar with this. Alkanes and chapter 10 and chapter 11, hydrocarbons are nonpolar. You're going to see they're nonpolar. Hydrophobic. Why? Because water is polar. Water is a polar molecule. It has some charge separation in it. The oxygens are kind of on the negative side. We usually put a delta negative there. Delta positives on the hydrogens. So the water molecule is got some poles to it, like a magnet does. It's got a negative end, and it's got positive ends to it. Hydrocarbons don't have that. This is flowing out, if you remember 1305, this is flowing out of electronegativities. Because oxygen has a very high electronegativity, the electrons are being pulled towards the oxygen, and electrons are negative. So they're flowing around that oxygen and making that oxygen appear somewhat negative and leaving a proton out here without an electron around it most of the time, and protons are positive. So they have a pole to them. Well, carbon has a much lower electronegativity, and a carbon-carbon bond, those two atoms have exactly the same attraction for electrons. So they don't create a pole, and carbon and hydrogen have similar electronegativities. Carbon has a little bit higher electronegativity than hydrogen, but not as great a difference as oxygen does. So these bonds are nonpolar bonds and making the molecule then nonpolar. This is why gasoline and water don't mix. You put gasoline and water together, gasoline's a hydrocarbon. It's nonpolar. Water's polar. Like dissolves like. Water is more dense than these hydrocarbons, and so water would sink to the bottom of hydrocarbons. Hydrocarbons would float on the top. The BP oil spill, the oil came to the top of the Gulf of Mexico. It came to the top because it's less dense. If that wasn't the case, it might have been 9 months before we knew that BP had an oil spill. It would have been spilling out into the bottom of the Gulf and dissolving there, or just staying there, lying there. We might, who knows when we would have learned about it, but it started coming, bubbling to the top. We knew we had a huge oil spill. This is just keep this in mind. We're looking at boiling points. Typically, as molecules get bigger and heavier, they have higher boiling points. We're talking about we're talking about the amount of energy to get that molecule to float around in the gaseous state, to be propelled up into the gaseous state. So the heavier it is, it's like a shock putter. The heavier that shot put is, the less he or she can throw it. So likewise, it takes more energy to get this is decane. This is what this is, number of carbon atoms. There's methane, ethane, propane, butane, decane. So decane has a boiling point of like 200 degrees centigrade. If you're below room temperature, what does that? That means that, and if the boiling point is below room temperature, that before you get the room temperature, it's boiling. It's a gas. So anything with a boiling point below room temperature is a gas at room temperature. And now pentane, hexane, octane, we're starting to get into liquids. Okay, reactions. Reactions. Let me just, you got the slide there, but let's just look at this. I'll tell you what we could do real generally here. We can say an alkane plus oxygen forms carbon dioxide and water. Any alkane. And this is combustion. And I'm going to just add this adjective to it, complete combustion. Complete. Complete combustion breaks it down into carbon dioxide and water. So we could just list a whole bunch of alkanes here, and we wouldn't change anything over here. We would just have, for example, methane plus oxygen forms carbon dioxide and water. Propane plus oxygen forms carbon dioxide and water. Octane, which is gasoline, plus oxygen forms carbon dioxide and water. So the methane you're burning at home to heat your home here in 2 or 3 months is going to be, the exhaust coming out of that is going to be carbon dioxide and water. What's coming out of the tailpipe of your car when you're driving is carbon dioxide and water. As long as you've found a gas station where you can get some gasoline. All right? I was very pleased last night that I did that on my way home. So that's good that you're all here. That means you all found gas somewhere or someone to bring you to school. There may be a whole lot more carpooling going on here in the next few weeks. Who knows how long this is going to last. Okay, now the thing we need to do now is balance these equations. So let's see here. Yeah, so what I'm going to suggest to you to balance these equations, this is what I teach in 1305 as well, so you may have, if you had me for 1305, we're not going to do anything differently here. Balance them in this order. The carbon first, the hydrogen second, and then tidy up the oxygens at the end. So what I have over here, there's a 1 here. So I got 1 carbon. So I'm not going to put anything in front of the carbon dioxide. I have 1 carbon. Over here I have 4 hydrogens. So I'm going to put a 2 right here so that I get 4 hydrogens. 2 water molecules. Each water molecule has 2 hydrogens. Would give me 4 hydrogens. So my carbons and my hydrogens are balanced. So now I come on over to the right side, the product side of the equation. I say, how many oxygens are over there? There's 2 of them in the CO2. There's 2 oxygens right here. And there are 2 water molecules. Each has an oxygen. So there's 2 oxygens there. That's 4 oxygens. So this is what I mean by doing the oxygen last. So each oxygen molecule has 2 oxygens in it. So what do I need to do in front of the oxygen? Put a 2 right there. 2 times 2 is 4 oxygens, and it's balanced. Okay? So what I expect you to be able to do is to complete a combustion reaction for an alkane and balance it. So let's do this. Write out the balanced reaction for the complete combustion of propane. All right, that could be a word problem on a quiz or an exam. Write out the balanced reaction for the complete combustion of propane. So go ahead and do that. Can I look at this? I just want to see if I'm covering everything. We've got isomers. Yeah, I think we're covering everything. What do you got to do here? Correct the
Namings.
Give the correct name. Okay, yeah. Yep. We got one more reaction to do. Okay. Okay, so propane is what? Where did this go? Just lost my. C3 what? C3 what? H8. Oh well. I'm doing it. Put them together? I don't know. Gotta. Okay. C3H8 plus oxygen yields CO2 plus water. All right, so we're going to put, we've got 3 carbons here. So we're going to put a 3 right here. 3 CO2s. We've got 8 hydrogens, so we're going to put a 4 right there. That gives me 8 hydrogens. 3 times 2 is 6 oxygens coming from the CO2. And 4 times 1, H2O1, there's a 1 there, not written. There's only 1 oxygen. 4 times 1 is 4, is 10 oxygens. So what do we need here? All right? Okay. Now, so that you don't get overconfident, do this one. Oh, that's going to be a 10. This is butane. So do that one. That would be the complete combustion of butane. And this one's harder. So how can it be any harder? How many of you have run into the fact already that there's an odd number of oxygens? Right? Okay, that's what makes it a little bit harder. So let's see how to deal with that. You may already know how to deal with that, but let's just look at it. Just start out the same way. I've got 4 carbons here. So I'm going to put 4 CO2s. I've got 10 oxygens here. So I'm going to put 5 waters. You see I got 5 waters over there. So now I got 8 oxygens plus 5 oxygens from the water is 13 oxygens. My carbons and my hydrogens are balanced. But 13 oxygens ends up being 6 1/2 or 13 halves, whichever one, however you want to look at it. It's 6 1/2. Or 6 1/2 is 13 halves oxygens. And that's balanced, but we don't like fractions as coefficients in this equation, because we're really going to kind of read it as a certain number of moles of butane reacts with a certain number of moles of oxygen to produce that many moles of carbon dioxide and that many moles of hydrogen. We don't like to say 13.5 moles of oxygen. And you can't get a half of an oxygen. So if you multiply every coefficient by 2, double the recipe, like you're making pancakes. So remember, in front of C4H10 is a 1, so 2 times 1 is 2. 2 times 6 1/2 is 13. 2 times 4 is 8, and 2 times 5 is 10. Okay? So just double all the, it's the only case you're going to be in. You're going to either have a whole number of oxygens, an even number of oxygens on the right, and you can get a whole number of O2 molecules, or you're going to have an odd number of oxygens on the right, and you're going to have a fraction, so you're going to multiply by 2. Okay, I called this complete combustion. I just want you to know why, what else there is. Just know that incomplete combustion is not a good thing. Incomplete combustion produces carbon monoxide and water. It hasn't completely burned, it hasn't completely oxidized the carbon to carbon dioxide. Oxidizing it to carbon monoxide is only partial or incomplete combustion. Don't worry about it too much. I'll usually, I will say, even if I said write out the equation for the combustion of, just assume I mean complete combustion. I think on your homework I did say complete combustion. So be familiar with it. Just know that you could handle this kind of an equation if it came on your TEAS test. You could handle it. You could balance it. You just gotta know and be aware of the fact that it's CO. It's not CO2. Okay, and finally, halogenation. So the two main reactions of alkanes are combustion and halogenation. Under combustion, we could talk about complete and incomplete, but the two main reactions are burning it with oxygen or reacting it with a halogen. Halogenation. And just keep in mind that halogenation can be any one of these 4 halogens: fluorination, chlorination, bromination, iodation. Those are specific halogenation reactions. And let's do a simple one. Well, let's look at this reaction. And this is the halogenation of methane. The class of this reaction, it's a substitution reaction. What do I mean by that? Substitution. So we're kind of classifying it a little bit here. A chlorine is going to substitute for a hydrogen, and a hydrogen is going to substitute for that chlorine. So you're going to get a chlorine on the carbon, one chlorine, and you're going to get HCl. All right, that's a balanced thing. So this is going to be CH3Cl plus HCl. And if you look at it, I've got two chlorines. I've got 4 hydrogens, 4 hydrogens, 1 carbon, 1 carbon. That's balanced. What's happened? A chlorine has taken the place of a hydrogen, and the hydrogen has come off and bound to the other chlorine. All right? So that is substitution. It's the halogenation of an alkane. All right? If this were propane, you could put that chlorine anywhere, just anywhere. It's going to take the place of any hydrogen. Probably, you know, wherever it can take the place of a hydrogen is probably going to happen. And then there's going to be HCl as well. So there's the halogenation of propane. That's the chlorination of propane, which the general reaction is halogenation. Okay? I think that kind of covers it. You can see you would end up with an acidic solution. You would see an acid being formed. That would be one of the evidences of this. This is an alkyl halide that is being produced. An alkyl halide. It's an organic, an alkane with a halogen on it. All right, your homework is due on Monday. And we'll start chapter 11 on Monday.
So would you name this methyl chloride or chloromethane?
Methylchloride.
Not chloromethane.
Both of those
They're
names.
the same?
Both of those names. I guess it would be chloromethane. Would be probably the IUPAC name. You don't need a number because there's only one chlorine in it.
But you would need for this one depending on whichever H
Yeah,
is.
yeah. This one would be either 2-chloropropane or 1-chloropropane. Right.
Thank you.
You're welcome.